Hi. So far we have discussed the zeroth and the first law of thermodynamics, whereas the zeroth law defines the concept of thermal equilibrium. The first law is nothing but a restatement of the law of conservation of energy. Now we are trying to understand another fundamental law in thermodynamics. I should say the most important out of the four laws of thermodynamics, namely the second law of thermodynamics. You will see that this second law of thermodynamics has been formulated in several ways. A number of statements exist for the second law of thermodynamics, and you will see that this law is stated in terms of another very important thermodynamic quantity namely the entropy, which we will do in the next module of this particular course. And in this particular session we will be discussing about two of the important statements of that law. Okay, now one thing I must say, that we always wonder why many of the processes in nature doesn't occur, even though we don't find anything which limits that process to occur. Like you always see that see, if you keep a cup of tea, hot cup of tea, open in the atmosphere, you always see that the tea gets cooler as the time passes, right? So the temperature of the tea gets reduced as the time passes, means heat flows from the higher temperature, okay, to the lower surrounding. You can see that, and we never observe, or it's so far not yet reported, a case where see you are keeping a cold sample of a liquid in a container and see drawing heat from the surrounding by itself, the cup of liquid getting hot. So means the reverse process are not observed. We always observe the process to be happening in a in a single direction. Okay, so we don't find many of the processes not occurring in the opposite direction. And what forbids it? Okay, why is there exist any particular limitation for some process in nature to occur? Why don't some processes which may otherwise occur is not actually observed in nature? So there are several such questions of interest, and all these questions of interest now has been answered in a single stretch by coining what is known as the second law of thermodynamics, which I told you is one of the very fundamental laws of nature. Okay, and for example, we know that the ocean, and the surrounding air is containing an enormous amount of heat. Okay, we call it as internal energy. And we can always think of a situation in which a boat or a ship is extracting heat from the ocean. Okay, if the ship is extracting heat from the ocean by itself, and it is powering itself, okay, and it is running, but we don't find, or so far we are not able to design an engine, or we are not able to design a ship which can extract the internal energy from the ocean and run by itself. Means by converting this heat energy drawn or absorbed from the ocean completely into work, it's not able to just do. Okay, so there are several cases where there is something which seemingly can happen, but it's not happening in nature. So we'll see a speciality with the second law of thermodynamics. The second law of thermodynamics is usually stated as a negative statement. It is given as a negative statement, and that is something notable. Second law of thermodynamics is a negative statement. So it says something is not possible or it is impossible. Negative statement. Okay. That is something notable feature of second law. It's a negative statement. It says that certain things are not possible. Okay, saying certain processes are impossible, and that is one thing that I do always remember. Certain processes are impossible. Okay, now I told you there are several different formulations of second law of thermodynamics. Means you can express the second law in different forms. One easy way to remember the second law of thermodynamics, to put it in a most easy manner, you can say that the second law of thermodynamics gives a fundamental limitation. It gives a fundamental limitation. That's the easiest way. Gives a fundamental limitation. You know, limitation means says that it cannot do. Okay, it's a negative statement. A fundamental limitation. A fundamental limitation to the performance of or working of two of the devices that we have defined, heat engine and the refrigerator. So that is the most easy way of stating the second law of thermodynamics. So the second law of thermodynamics gives a fundamental limitation to the performance of a heat engine and refrigerator. See, I have already just put it on the slide. These are the statements. Okay, these are the easiest statements of second law of thermodynamics, even though it is not a textbook definition. See, one thing, the second law states that the efficiency of a heat engine can never be unity. That is one way in which you can express the second law. Efficiency of a heat engine can never be, you see, this is why I told you that it's a negative statement, can never be unity. Unity means one. Okay, right? See, it can never be unity. So let me there. Right? Okay. So let's see why it is so. Just a moment. Yeah. So it can never be unity. So let's discuss what's the meaning. So you know, from the theory of heat engine, we defined the efficiency for a heat engine. Efficiency eta, how it was defined? That was defined as the work output, right? So you can see the schematic diagram of the heat engine on the right side. So this is the output, work. So you know, eta is always equal to what you get by what you give. So output by input. So W, that was thing, divided by what is the input. Input means what you are drawing from the low temperature reservoir. So QH is your input. So I can say W by QH. I'm not using the usual modulus symbol and all. So which you know, we have modified it earlier. W can be written as, okay, it will be the difference between QH and QL, right? So I can write as QH minus QL, QH minus QL by again QH. This already had done. I'm just repeating it for the time being. So it can be written as finally 1 minus QL by QH. That was our definition. 1 minus QL by QH. Okay. So this was our expression. So what is this statement telling? The statement says that the efficiency of a heat engine can never be unity. It can never be unity. So it says that eta is never equal to 1. 1 means 100%. So it says that basically you cannot have a heat engine which is having 100% efficiency. That we already have seen in our previous discussions, because you won't be able to convert heat completely into work. That is where we discussed, or we started our discussion of this particular module, right? So eta is never equal to 1, or eta can never be equal to 100%. That is what actually the statement. So it's a negative statement. So let's say, let's see what does it mean. So it means that see eta, see that for example, if you look at this expression, for eta to be equal to 1, for eta to be equal to 1, what should happen? So you can see that this QL should be equal to 0, right? If QL equal to 0, eta can be equal to 1, right? Then the second term, this subtracting term will be equal to 0. So I can say that it means, or this statement means that QL is never equal to 0. That is another interpretation. QL for a heat engine can never be equal to 0. QL can never be equal to 0. That is another simple way of putting the the statement of second law of thermodynamics. So just look at the schematic diagram. What is this QL? The QL, as far as a heat engine is concerned, is the amount of heat energy that is rejected to the sink or the low temperature reservoir, right? So this QL can never be equal to 0. It's not equal to 0, right? That fundamental limitation in the working of a heat engine is one of the statements of the second law of thermodynamics. So if QL equal to 0, then entirely this QH will be getting converted into work. That is why it is happening. So then in that case, eta will be equal to 1, or efficiency will be equal to 100%, right? It can never happen. So all these interpretations are there. So it means that in a heat engine, you must have, say I'm pointing out, you must have a low temperature reservoir to which a non-zero heat can be rejected. The presence of a sink is a must. Okay, so it denotes that sink is a must. I'm putting the same statement in different ways. Sink is a must for a heat engine to work. Sink is a must for a heat engine. Okay, so there must be a sink or a low temperature reservoir to which certain amount of heat can be rejected, right? That should always happen as far as a heat engine is concerned. So that is the meaning of the first negative statement. Now let us come to the second second negative statement of the second law of thermodynamics. That is, let's read it. So the coefficient of performance, you know, this is the quality factor for a refrigerator. The coefficient of performance of a refrigerator can never be infinity. So here also you can see that can never be. This is also once again a negative statement, and that is a interesting feature of second law. Both are all, wherever or however you just state it, in different ways you can state it, but all these statements will be some sort of a negative statement saying that something is impossible. Okay, so the coefficient of performance of a refrigerator can never be infinity. Let's see what's the meaning, or let's try to interpret it. So for a refrigerator, okay, for a refrigerator, we are trying to understand in terms of what we already know. Okay, what is coefficient of performance? Omega. Hope you remember it was represented as COP or omega. And what is omega? I told you it is just like an efficiency as far as a refrigerator or a heat pump is concerned. Okay, right? So what is that? What is the desired output? What is the desired output? So in order to remember that one, if you don't remember, it doesn't matter. You recall the the schematic diagram, which I have again reproduced on the right side. This is the second one is the diagram, right? What happens here? Using work done on the system, right? Here work was done by the system, you know, heat engine. So heat QL is absorbed from a low temperature reservoir and it is rejected to a high temperature reservoir, adding the work done, right? So, you know, our purpose is to cool down, means you have to further reduce the temperature of a already low temperature reservoir. So this is your desired outcome. I need not say the word output, better thing can be an outcome. So my desired outcome is QL. So what is omega equal to? Omega equal to the desired outcome. I can say QL divided by what you have to pay for it, right? What is the input? So the input, you know, that is the work done. You are giving some electrical work, Okay, you are giving work and you are removing heat energy. So the input should be the W, right? So QL by W. So now it's very easy. Okay, what does it mean by saying that omega of a refrigerator can never be infinity? So let's think of that, in which case this omega will be infinity. Omega will be infinity. One easy way is that when you say that this the denominator here is not, so it will tend to infinity. It will tend to infinity when the denominator tends to 0, right? If the denominator tends to 0, if denominator means work tends to 0. If work is 0, then omega is what? Infinity. So what does it mean? It means that without work, without external work, okay, without doing external work, you can never transfer, or we can never absorb heat from low temperature reservoir to high temperature reservoir, and that is a well-known fact. Okay, is it not right? Because you know that the spontaneous direction of flow, or the direction of spontaneous flow of heat, is from high temperature to reservoir to low temperature reservoir. Okay, so if heat has to be further removed from a already low temperature reservoir, there must be some external aid, and that external aid, you know, that comes in the form of what? Work done, right? So the coefficient of performance of a refrigerator can never be infinity. So omega is not equal to infinite. For any refrigerator, omega will never be equal to infinity. For omega to be infinity, the work input should be equal to 0, and you know that with the 0 input work, it is never going to happen, because it is against the direction of flow of spontaneous flow of heat. That is why I told you that, okay, the second law of thermodynamics is actually giving you the explanation why certain things does not occur in nature. That is why I began with the example of why always a hot cup of tea getting cooler as the time passes. Why don't a cold cup of tea is not getting hotter by absorbing heat from the surrounding, because there is a lot of internal energy in the surrounding air. Why can't the system absorb automatically heat and boil itself? You imagine such a situation, okay, like a film running backward. Okay, why can't a cold cup of tea absorb heat from the surrounding and start boiling? Then it would have been very nice, right? Okay, so that doesn't occur in the nature. Why such processes are not occurring in the nature? Of course, okay, this thing is basically, now you can give an explanation that it's a fundamental law of nature, okay, and the nature doesn't allow everything to happen, and that is the way in which you state it now. Okay, so and why it doesn't allow, right? That is always a question. You can always question that. Okay, why doesn't the nature allow certain things to happen? And in order to explain that, in order to justify that statement, we will have to define another very important quantity, and that quantity is what is known as entropy. I told you second law of thermodynamics is better explained in terms of a quantity known as what? Entropy. Okay, and that will be doing in the next module. Well, right? So that's the fundamental idea regarding the second law of thermodynamics. And remember, this is one of the way in which you can state the second law of thermodynamics. As I told you in the beginning of this session, the second law of thermodynamics can be formulated in several ways. So what we have tried in this particular session is to put the second law of thermodynamics through the angle of two of the machines that we have already learned. One is a heat engine, another is a refrigerator. We tried to explain the second law of thermodynamics by putting two conditions on the working of a heat engine as well as a refrigerator. So basically, we can say that the second law of thermodynamics gives a fundamental limitation to the efficiency of a heat engine and the coefficient of performance of a refrigerator. Simply, it says that the efficiency eta of a heat engine can never be equal to unity, or QL is not equal to 0, or I can say that sink is a must. There should be a low temperature reservoir. You cannot have a single reservoir heat engine. That is not possible. And the coefficient of performance of a refrigerator can never be infinity, which means that without an external work done, you can never ever transfer heat from a low temperature reservoir to a high temperature reservoir. Okay, so these are the ways in which you can explain the second law of thermodynamics. We will see more concrete forms of the definitions of second law of thermodynamics in the next session. Thank you.